speedy traits. And we see there are more need for other traits, insect-control traits, to control the secondary insects and the new insects. So it's the spectrum will be broader. And also, the industry is also want to have a reduced refugee, so we have to increase the yield. So in the last 15 years or so, we have seen already benefits. I mean, on the biotech traits. One is for the reduced chemical inputs, and so not only the amount is reduced, we have to spray less, and also it's easier, like glyphosate, spray, the herbicide spray. And also simpler farming practices, as mentioned like yesterday, and finally, of course, the increase the yield. So in Syngenta, we are using an approach, integrated approach, incorporating not only biotech traits, we are using breeding, native traits, and also traditional chemicals, so to control the pests and also achieve stress tolerance and other agronomic performance. So especially this example is in corn. So in corn, we are facing a lot of insect issues, and especially even Lepidopteran. So the main problem with insects, they are not predictable. They're seasonal, it's always there, and it's very challenging to have an effective control for the using soft and especially beetles to control them with foliar insecticide. So if you look at the figure, especially the below, you can see from the corn germination all the way to the maturity. You can see there are many insects from the a black cutworm, the first one, basically the above ground insect. There are quite a few of them, from corn borer, European corn borer, and the fall armyworm and earworm. And on the underground, there are a lot of beetles and rootworms. And the corn rootworms is I think it's specific to the U.S. I think it's not here, and but there might be other kind of beetles though. So all those we call those insects as a multi-pestic complex. In America, it's costing a lot of money, farmers a lot of money. About the loss is about $1.1 billion annually in yield and grain lost. It's not only the yield is lost, it's also the quality, because if you have like a earworm infestation eating your corn ear, there's fungus will grow. There will be increased level of mycotoxins, so your grain quality actually is lower with the insect problem. So like in Syngenta, we develop traits in the middle, like here. And so we have Agrosure traits, and one of them is called 3111, the trait stack. So you can see by stacking our Agrosure traits with pterogenes with the traditional Crivine AB, so we're able to control the major 7 kind of insects, 7 insects labs. So you can see compared to other companies' traits, we have a very, I think, industry, very outstanding leading traits in controlling all the insects. So especially on the like western bean cutworm, black cutworm, fall armyworm, and the corn earworm. There's a remarkable control. Yeah, if you look at the competitors' traits, Herculex, and also the Monsanto's traits, so you can see we are head-to-head with them, and it's very competitive with smart stacks. So even for the corn earworm, the Viterra, that trait actually has better control compared to smart stacks. So in the next, those are some of the traits either has been on market, like the first one is 3110 Viterra. It's on the market already, so it has the stack of 1 is for the MIR 162, it's a Viterra trait with plus BT11, that's a Crivine AB. So it controls both the European corn borer and also broadleaf species. And also that product has both herbicide tolerance trait, the 2 mode of action. And the one I just showed previously is a 3111, and has not only the lab, but also has the Coleopteran, the rootworm. And for 3220, we will have additional like a 2 mode of action for both broad lab and the ECB. So this one is basically stack our own trait with Herculex together. And we're also developing other traits, 3122 and 3222. So you can see the target mode of action is basically more mode of action. And so last one is Agrosure Duracay 5222. That one is going to be come out in the next few years. So you can see the 2 mode of action for both the broad lab and the ECB and the corn rootworm and the herbicide tolerance. So again, with just to mention the Viptera trait based on the VIP protein, it's a broad spectrum control of above ground lab insects. So you can see, especially for the corn earworm, and the photo on the right. So the one on the upper corner, the ear is with you can see it's a very clean corn ear with no insects. If you look at the lower corner, that's the ears with basically the hybrid without the trait. You can see the earworm infection. So you can see that there will be a fungus growth, and your grain quality will be lower. So on average, nationally, it delivers about 7.3 bushel per acre under ear feeding pressure. So it brings a significant value. And so this is another figure showing that it's outstanding control of earworm. So there's a few ear damages and less damages per ear too. So look at the Viptera trait versus the control, and also the mycotoxin level, it's much lower. And with the Viptera traits on the upside, without the Viptera, the mycotoxin level it's much higher. With the traits, it's only 0.88 ppm, but without that, it's 4 ppm. So it's a significant benefit reducing mycotoxin. And also, that's another slide showing that from another study, reduction of aflatoxin using with the Viptera trait. And so this is basically a field testing of controlling Viptera trait and with the competitive product without the Viptera gene. So you can see the early phase of the corn growth, it's much better with that Viptera trait. And so I'd like to mention this, those Viptera is basically for controlling the labs. And next one is basically we also have the new traits coming out that controlling the corn rootworm. It's an event, it's called 5307. It's based on the E. cry31 AB protein. It's a different mode of action compared to our previous rootworm gene. It's called the MIR604. So it's so let's compare to our previous trait, the rootworm. It's Agrosure rootworm. It's based on MCry3A, and so the new trait, well, 5007 is based on a hybrid toxin, and so those two genes have two different mode of action, so it will give us additional control against the corn rootworm. So you can see the control on the right versus the plant with on the left with the new traits. We call it Duracay. And on the left, it's a field test this year. It's early in July, so you can see on this year in Illinois, Bloomington, Illinois, it's under severe drought. Under severe drought, that condition has a very heavy rootworm infestation. So you can see on the right, under that kind of dry condition, the corn, it's like a wilting. It's not showing very good sign, but on the left, it's very happy. And if you look at the root, on the left, it's a check without the trait. the root is heavily damaged by the rootworm, but on the right, the corn plants are really happy. It's big roots, and the big roots give you a big yield, right? So yeah, basically this is the if you count the number of beetles from that Western corn rootworm. So on the first bar is the iso line without the trait, and on the second one is MIL604. That's our event that's already on the market. And you can see it's even that existing event has a very good control already. It's significant. It's much reduced. But if you look at the second one, it's 5007. The new trait actually has even better. And if you combine those two together, it's even better. So it will be a remarkable trait for corn rootworm in the future. Yeah. So it will be released in the next few years. It's still in the late stage of development. It's not on market yet. And so I just want to mention that, since we're talking about stack trait, we are not only having the insect trait control and herbicide tolerance. In Syngenta, we already developed some of the traits for bioprocessing. There's enologene for starch, the ethanol production. So it provide a very good benefit on reduction in the energy costing when you produce ethanol. So we have all those traits. We need to stack them together and how to bring them together. And traditionally, all the traits I just mentioned, all those lab and the corn rootworm, also ethanol processing traits, they are all single trait locals. So we have to do them through just traditional breeding stacks. So breeding stacks has an advantage. It's very flexible. So like in areas you don't have like corn rootworm, like in other part of a country, even U.S. Because the corn rootworm is mostly limited to like corn belt, but in the southern part of the U.S. it does not have the corn rootworm. You don't need that trait. There's a flexibility. You don't need to that. Then you just do the breeding. You don't incorporate that trait. So it's a flexibility. And however, the traditional breeding method of incorporating that, once you have your number of traits more than 4, it's really very limiting, because when you're breeding more than 4 loci, and this is basically number of transient loci and versus the number of plants you have to screen. So if you have like 8 loci, then you have that number on the 99% confidence level. You have to screen the 660 kind of plants to find the plant that have your gene, all the genes. So it's because really limiting. You have too many traits. So the direction in the industry is you are combining all those genes into a molecular stack. So it's easier to breed, and especially considering you have hundreds of hybrid to convert. If you have more than like 4, 5, 6, basically your cost of goods is so high, you don't have any money to earn. Because the hybrid is turning over every few years, then you have to do it at those tremendous amount of introgression every few years. That's not sustainable. So industry is more or less moving into a direction of molecular stack. In addition to the transgene stack, we are also develop a lot of traits, like native traits. This is one of the traits in the Syngenta was developing. It's for water optimization, drought tolerance in corn. So we are doing that with a breeding approach. The native trait provided using Monsanto's transgenic, but this native trait is not single gene. It's more than 10 genes. So how you are going to do your molecular, the normal breeding of the traits in addition to this native trait together, that's almost impossible to do, and it's very costly. So we have to do a lot of molecular stack. However, the molecular stack is it's not as easy as you think, and normally we're just thinking, well, you have your trait cassette, one gene, the BP, and you have a lab, you have a VIP gene, you have other genes. You can just simply put all the single cassettes together, and it will give you the trait. give you the stack. Actually, it's not the case. It's much more complicated. And the main problem with that is the potential, the bottleneck is of molecular stack. We don't have a sufficient knowledge of optimal expression of performance of individual trait cassette. Normally what we do is individual traits, you just transform your trait cassette into corn plants, you generate hundreds or even sometimes thousands of plants. But if you combine them together, you can see the chance, right? You have 1 out of 100 times 1 out of 100, maybe. That's 1 out of 10,000. That's if you have 3 or 4, it's hard to do. And also lack of understanding how individual cassette will interact when placed in close proximity, especially impact on tissue-specific like gene expression, and limited choice. Use of same element sometimes and result in erratic gene expression in multi-gene stack, and also how to efficiently deliver large molecules in multi-trait stacks. And talking about the delivery of a trait, so normally we do a transformation these days with Agrobacterium Mediated transformation. So I have a table here showing basically this, the size of tDNA and how, as you increase the number of genes, what are your efficiency in transformation. So the first row, the second row, it's when you have a 6-gene expression cassette, right? So the tDNA, it's not that big, it's about 22, 23 kb. So you have a reasonable efficiency, around 15% transformation efficiency. However, if you increase the number of genes to like 11, so you can see that's about 40 kb-ish. And then the efficiency dropped to about 8-9%. If you further increase to like about 30 genes, 27 genes, and 20 gene individual cassette, 27, the gene size, tDNA says about 100 kb, 113. So the efficiency dropped to about 1%. So 20 genes, it will be a while before we reach it, but we will probably reaching that maybe in 10 years and or maybe 15 years. And because especially some of the traits like a drought, you may need a pathway, multiple gene. If you combine multiple together, you reach that number of genes pretty fast. And another thing is about the potential effect, and because not all even you select all the transgenes, single copy transgenes, the expression is still varies among the different transgenes. So you can see that the 2 genes on the tDNA, it's 1 gene, like on the blue one is on the close left border, and the green one on the right border. This is one of the construct with the 11 genes stacks. So you can see that the expression is still variable, even though they are all single copies. And so how do you control that expression? That's the big question, and we don't have an effective tool. This is basically based on the insect efficacy of those events. So you can see on the left panel, so it's the wild type, of course, the insects, they're like 2 genes, one on the left, one on the right. One is on the prime one. AB is controlling that's on the upper petri dish. Lower one is another worm, it's a black cut worm, VIP3. So you can see only one or 2 of the events have a good control, even though they are all single copies. They show expression, but not all of them have a very good efficacy, right? Only 2 of them looks like good efficacy. So I think it's so that normally what we do in molecular stack, of course, now it's the kind of flow. So in the first we start with a combination of a trait combination selection. And we test our single cassette, including like the design and the validation expression, checking out the open reading frame, toxin allergenicity, homology check before we go further. And then we do if the single cassette works well, we do the stack design validation. expression profile and run the same toxin and allergenicity homology check, and then we do transformation, and then we do event analysis and do efficacy, and before we go to the even doing the field testing, and we do the coding sequence and the flanking sequence analysis before we do the field trial. And finally, out of those many events, we've selected a few for further characterization. So one of the typical flow, actually, this slide showing that even with like 2 genes, 2 insect control genes, plus the marker, this is 3 genes. So we usually generate hundreds of corn transgenic plants, and we select about dozens or up to hundreds to the field. And then we finally select a few lead events to do product development studies. So that's the kind of effort that you need to get. So I think for one of the things that we mentioned is we don't have an effective control of position effects. That's a question actually. If we have the tool control, that will reduce our effort a lot. And in the past 10 years or so, there are a lot of effort on how to do like a molecular stack. It's the better way. Of course, I mentioned this large tDNA. Another thing is people talking about different tools on using site-directed integration, including like some logs or homology combination, and also mini chromosome, and also plasmid transformation. And recently, the tool has been developed as a tailor-mediated targeted insertion, and or zinc finger is very similar tools. So it will be interesting to see if we can create site-specific integration events that those will reduce the variation and reduce our effort or not. So it will be kind of interesting if you compare the tools with large tDNA versus mini chromosome versus zinc finger meganuclease tailor-mediated integration. So they're supposed all of them have some pros and cons. I think, of course, on the large tDNA or just normal tDNA, it's very routine now. We can do it. But it's still give us a random insertion, unpredictability of the trait efficacy. And mini chromosome is still too early. I think it's a very complicated technology too, and also for the like a meganuclease targeted insertion, TALEN. So we have to see its the efficacy to see we can have a reduced effort. But those are basically the tools we have in the future for molecular stacks. I think that's all I want to say. And finally, I want to acknowledge people from our like Meridel and Zong Yin and all those my colleagues, and help us doing all those efforts in doing molecular stack, and of course my management teams and nice people. I think that's all I have to present, and if you have any questions, I would like to answer that. Thank you very much. Yeah.